think this is the only loop really where it matters. The second loop, all primes are I think all primes are larger. Oh, this literally says here larger than the compression primordial, so large. So yeah, and then we add prime to the word pointer, to the row pointer, whatever. So, well, at least in the inner loop, which step equals prime. Well, that's what we add. So if this is over 30,000, then yeah, we'll just go out of whatever L1 cache we have here. Even if words is a character. Well, almost done. But unless I reduce the compression, of course. But, okay. Definitely the most important loop is this one. And apparently I want to... It's completely impossible to get normal music here. I keep clicking thumbs down. Right. I do not want to do any memory access beyond L1 cache, which means for the whole loop. I think. Where's my column? I suppose column, oh, here's the column. Column is 0. And then this loops over. Word index is just the index into the sieve. Yeah, right. The first, this is just row 0. Excuse me. I have two rows. This is row 0 and I pick up from that the primes, and then after that I'm going to fill columns with, and that would be col. That's what I have to concentrate on, not the outer loops. So once I have a prime, and only once I have a prime, yeah, I need to limit this and then later pick it up again where we left off. So I guess I need to remember call mask and WI and word step. More for debugging purposes. I don't know. Doesn't feel like it would be very much faster. Oh, shit. Yeah, okay. Hello. I think I have to change that as well. Is that the only one? Probably the only one. No, that one's there too. And 143, yeah. Well, let's go to the smallest compression that still has this. Can't go smaller. Yeah, those are all primes. Those are all primes. So I'll have to do 4. Of course I would. It's fun. It's just the best language. In terms of fun, it's the best language. These non-primes should not be there. I mean, it just doesn't make any sense. What happens if I remove them? Yes, it is. It's very hard to do something. Yeah. You need a very large amount of code before something starts working. But it is fast. Mm-hmm. Well, JavaScript is about the worst language you can think of. It's pathetic. JavaScript. Dude. At least go for Python then or something like that. But at least I'm the first to admit that you're right, that C++ is very slow in coding. And yeah, just a high barrier to begin with programs that do anything useful. But I would like to think that in the end, programs have to be or should be written in a language that uses not much energy for what they do, aka than C++. If the whole world would be doing crypto in with JavaScript, and yeah, right. So when it becomes important that things are really fast, and or you just need to run it on many computers, like over the whole world, then you need C++ for sure. I'm eating my last orange. You know, I'm starting to dislike this this work here, the prime stuff. It takes too long. Probably should give thumbs up as well on music. That is good. I'm not going to do this. Plus, I'm now thinking that maybe it is correct, actually. For example, this contains 121. It's 11 squared. And the primordial that belongs to this is 220, 200 and something. That is 2 times 3 times 5 times 7, 210. 210 plus 121 is what plus 121 plus 210. Yeah, it was 331, which is a prime. So that is it is required, this number. I'm wrong to say that it has to be prime numbers. Good. Well, then. Wyszynski, hi man. I'm just not getting better, it seems. Yeah, that's well. It's good to hear, Wyszynski. Cool, man. Try to be curious. When they tell you something and then yeah, the right feeling is like, oh my god, this is so interesting. I want to know more about it. Talking about which, I wanted to know more about the Atkin sieve. And I did look into it a bit earlier today. And I feel like going in that direction instead of, I don't know, changing these loops. Who cares? Or maybe I can get this like 10% faster or something like that. I don't believe in really big steps anymore. I'm done with it. It's just not worth my time. Should do it for fun, right? Yeah, and then I should probably, add threading to it as well, which then would make it a lot faster. But it's a lot of work, and I just don't feel like it anymore. So right now we have this 10 billion. All numbers still 10 billion. Well, all primes still 10 billion. It's not something you would want to wait for at the start of every time you run a test program. 20 seconds. But, well, Maybe I should just run it once for all prime still trillion, and then write it to a file, and then I just have them on disk. Period. Let's look at this the Atkin stuff. That's just interesting. It's math, but well, maybe even make it larger. On. Dark is better, isn't it? So I was looking at this proof here. Let n be a square-free positive integer with n congruent 1 modulo 4. Then n is prime if and only if the number of solutions for positive x and y of x 4x squared plus y squared is n is odd. Well, that's a bold statement, and as a programmer, I think we should test that to begin with, you know. For small numbers, just get an idea of the exact values that go into x and y here. Let me edit an Atkin 3. Well, my computer can go to, I guess let's do n is 1 to n less than 1000 to start with. Then obviously, if let's do everything positive. Oh well, I'm going. Let's go to 10,000. Then obviously x must be less than, well, actually the square root. Let's just add a square root of 1000. I'll make it a constant. Max n. Actually, I need C math. I just need the square root of n. The square root of n is standard square roots of n. What else could it be? Now, if you look at this formula here, then if x is too large, then it's never going to be a solution, no matter what you pick for y. Y is not complex, so this is positive. So yeah, but I mean, it doesn't make any sense to, let's turn it around, to have y larger than the square root of n, right? Because x and y are larger than 0, so the minimum value is 1. Let's just fill in 1 here. Let's copy this, so you know what we're talking about. We're going to try this formula here. Test it. So what follows from that is that, for obvious reasons, yeah, x and y larger than 0. For obvious reasons, then x is less than the square root, or less than or equal the square root of n minus y squared divided by 4. And the minimum value y is 1, so x is less than or equal to that, right? So we can calculate for one now we know n, because we turned the stuff around, I think, or not, well, I don't know. We know n, that's the outer loop. So I can calculate, let's call it limit x is, well, that. Now this returns, I think, a float. I'm not even sure actually, so I'll just look it up. Or a double or something. Yeah, it depends. Positive and integer, so the integer is going to be converted to, I don't know. Okay, it's a floating point, some floating point, divided by 4, and then we take the ceiling, the floor, by assigning it to an int. Okay, let's do it like that. Too precise, I don't know. So now we must be less than or equal, because this is already the floor of that. And that's the whole range that we should test, because if x is larger than that, then there's never going to be a solution. And we're trying to count the number of solutions. And y is also positive, so it starts at 1, and then y is less than or equal limit y. Yeah, just subtract this from n and then take the square root, and then we have the maximum value. That makes sense for y, because if y is larger than larger than n even. So not also a minimum value then? That makes sense. I wouldn't know. It seems to be the right choice. Okay, now if my formula, so 4 times, well, I can calculate x outside the loop, although outside the loop of y, although the compiler is probably going to optimize that anyway. Let's just put it in here. 4 times x plus y times y equals n plus plus solutions. So we're going to try for every n between 1 and 1000. Well, we're not actually, but okay, let's add that test as well. It must be congruent to 1 modulo 4. So if that's not the case, then continue. I think that just means that we have to do n is 1 and then we continue with n plus is 4. Right? Don't do test it. Yeah, that was this demand here. So n is element of 1 plus 4 times z. That includes negative numbers, by the way. But that's because they are going to do stuff with complex numbers later on. But yeah, it's kind of nonsense because they say x is larger than 0 and y is larger than 0. So guess what n is? I mean, even if x and y were negative, that's still. There's nothing. This sentence here has nothing to do with complex numbers, so I don't know why they use z there. Anyway, we start at 1 for n, and we add 4. So then modulo 4, n is going to be 1, right? So that's what it says. It's 1 plus some number, some integer times 4. Dude, I'll never get better. I'm coughing again. It's lack of sleep, I tell you. It's really bad. Okay, and then we print n, followed by the number of solutions for that n. Well, it's not a lot of solutions. It's either 0 or 1. It's never a double solution. What the hell? Oh, here's one. 2 solutions. Wow. Almost all of them are just 1 solution. So useless. Well, that's... I don't know. Is that a prime? I need an is prime page. Web page. What kind of interface is this? Numbers? Put from file? I agree with all the cookies. Primarily the test, yeah, that's for big numbers. What about that? Composite, it's not a prime. Okay. Could have factorized it for me. Well, that's correct then, I guess. not a factorization. Oh, I can use wool from alpha. Oh, factorize. Ja, dat check het ook. What was the number? 629. 17 times 37. But yeah, now we have to check all the others as well. I just need a prime check, like, is this a prime number or not? I wrote a lot of code about generating prime numbers. Maybe I should just add it to my utils and I can use it. Let us think. In the end, I guess there's several interfaces that I might be interested in. One would be generate a vector with all primes, and then we have just an interface that now I can ask, is this number a prime or not? And an interface where I can just ask for the next prime. So then it would not be stored in a vector, but I can ask for the next prime. I think I'm going to go for that. It means that I need, I think, a sieve. Something that returns or stores, just stores, I guess, a Bit-sieve. A bit compressed as well, not maximum, but well, pretty compressed. And then let's initialize it with all zeros, I guess, maybe. Yeah. And then I'll just set the bit when something is a prime, instead of storing the primes. And I have a double sieve if I'm using a more compressed sieve to generate them. But I won't have a vector to store the primes in. So it's probably not that bad. I'm putting it in utils, I think, for now. Seems reasonable. Or maybe I'm should not put it in utils because how do you call that? Spamming. Too much junk in utils. So the max value is the maximum value that that it will work for, and then we have stuff like is prime, and next prime. I'll just call it next prime instead of just next bit short. Now would you use internal something so it's not const. So I keep calling it, I get the next prime. Maybe I want to start over as well, so I'll probably need a reset. Did it say anything else? I don't think so. I think this is it, right? It's the whole interface that we need. Maybe a special exception clause to throw if n is too large. They can just throw out of range. Okay. And then internally, it's gonna store I think a bit set. No, that doesn't work. So a bit set takes it's not dynamic. So then you cannot pass max value. Maybe I should use a bit set and then just make the primes thing a template. So you just pass max value as a template parameter. Why not? It's not like I need a lot of them. Suppose you want to have a primes with a max value of 1000 and you want a primes with a max value of 10,000. Then you're an idiot. Because you can use the one with the max value of 10,000 then instead of the one with the max value of 1000. Every program only needs one primes object, so might as well make it a template. And then it becomes a header only thing. People seem to like that. So let's do that. So the constructor is existing. The rest stays the same. Now we can use a bit set. With some size. And we call that, I don't know, it's a bits. The bits are set when it is a prime. But shall I call it a sieve? doesn't really matter, it's private anyway. Now I could of course use max value here, but that would be a bit silly because that includes all the even values. So we want to use something like divided by 2, then we get rid of the even values. Might as well make that public. Sieve size. Yeah, God knows who wants to use it. So what's the sieve size now? I think that it gets a bit complicated to make it very compressed. But I have the feeling I want to compress at least 2 and 3 out of it, and maybe also 5, if that's possible. If that improves stuff. So if you remove all even numbers, then the size gets cut in 2. That's like multiplying the size with a half. And then if you remove all numbers that are divisible by 3 still, you multiply the size with 2/3. And if you remove all numbers that are divisible by 5, you multiply it by 4/5. And then 6/7. So yeah, at some point, yeah, you know, I mean, the amount of complexity gets too big for what you win. I think if I continue this to 17 or 13, 12/13, then it gets 30% smaller. So let's keep it at this, I think. Okay, but that means that we need to make a mapping of the actual n to the bit index. And we removed all numbers that are, well, probably don't need to put 1 into it either, but okay. At the very least, we removed all numbers that are divisible by 2. And we removed all numbers that are divisible by 3. On top of that, so that would be that one. So the only numbers that are left are, now okay, let's put 1 in it as well then. So that would be index 0, and then this is index 1. Okay, let's not do 5 yet to see how this works. And the way to calculate, to convert n to bit index is then with the formula it's just divided by 3, right? N divided by 3 gives the index. I'm gonna need add a few more. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, okay. And then we removed all the even ones, so bloop. 3, 6 down is 9, 6 down is 15. That's division by 2 again. So the bloody things are all primes for logical reasons, except the first one that isn't is the square of 5. But yeah, it's already easy to see. Well, it's already possible to see how to convert between the bit index and n. Well, what do I want to know? Something about, well, that would only be is prime, right? So if I want to ask, so is 9 prime? Well, if I divide it by 3, like I said I would, then I get 3, and I check that, and then it says, yeah, that's prime. So I need to know that 9 is not 11. I think I need to do a modulo 6. Yeah, because this starts to repeat every 6. So this is like 1, and then we do plus 4 is 5, and then plus 2 is 7, plus 4, plus 2, plus 4, etc. So it repeats after 6, so we should be able to see which one it is. If I do the number modulo 6, let's add modulo 6 of n as well. So n mod 6. And so on. I can copy that now. Y, P, oh, that moves everything. So if mod 6 is equal to 1 or 5, then it's possibly a prime. Now we can look in the sieve. Oh, there's also 5, 1, 5, 1, and so on. Any other number means that it's just not a prime. So first I would have to take the modulo 6 of it. And then yeah, then just divide by 3, I guess. 7 divided by 3 is 2. 5 divided by 3 is 1. 1 divided by 3 is 0. 11 divided by 3 is 3, and so on. That works. I'm thinking about if it cannot come. I don't know why, but I think that doing a modulo and the division is maybe as annoying me. I'm thinking about if I cannot do just one of them. How about I just do division by 3? Yeah, let's not think too hard about it, because I want to go to removing the 5 as well. I'm pretty sure then we have to do a modulo 30. To find out if it is even makes sense to look in the sieve. And then how to convert that. Dude, it's ridiculous. The table is not long enough. Yeah. This gives me always a lot of insight, but in the end, when it gets too big, you just have to use mathematics, I guess. Let's try that. Okay, so we have a number n. That's this n here. And I want to convert it to an index such that we skip all numbers that are divisible by 2, 3, and 5. See, that's absolutely not easy. Table lookup. Looks like it. Okay, so the compression is that, which is 8 divided by 30. It's 4 divided by 15. It's not even an integer. It's not even an integer. See, only the first two is a half times 2/3 is 1/3. So that's 1 divided by 3, and 3 is an integer, so I could divide by 3. But if you multiply that with 4/5, yeah, you get 4/15. So I would have to dragging floating points and then rounding it in order to do that conversion. That sucks. Plus it doesn't make any sense. I think I'm just going to divide it by 30. The modulo of 30 and divide by 30. You have to divide by 30. And then it repeats, and then the modulo over the table lookup. And then we might as well add 7 and 11 and 13 and so on, except that the table becomes extremely large. Let's make the table maximum 1 cache line, or is that too small? What do I want to store in the table lookup anyway? I think characters 1 byte is enough. So 30 bytes. And the next one would be 7 times that. Which still fits as an unsigned char. So then we are talking about 210 bytes. How big is a cache line? I forgot that. I think less. Thought I had it stored here somewhere. Crap. Nope. Cache line size, yeah. I was looking for cache and I didn't find it. Why? Because I did star edge. It was star edge.in. Bum, 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 bum. 64 bytes. That's not big. Okay, so the 30 bytes would look into. I'm going to make a table, I think, aligned at cache size, obviously. How do we do that? I must have code already that does that. It's not an align is. Projects. No, I guess this one maybe. That is the. Yeah, align is. Yeah, array. The bloody color pool did contain it. I thought, no, it cannot be. Cannot be that that's talking about cache. But it did. Okay, so a const expression that is aligned. It's kind of silly, I think, because in the end it must be stored in memory anyway. The whole idea of the table lookup. And now I'm not sure that I can add the align as here. So what is this going to store? Unsigned cards. And the size is then the primordial of 5. Well, let's use 30. No, never use constants. So we have a static const expression, well, literals anyway, literals. Primorial of 5, 2 times 3 times 5, that's 30. I keep forgetting my types here. Okay, so that's primorial 5. Might as well remove the 5. I mean, it's just the primorial. Not storing integers in the sieve that are divisible by 2, 3, or 5. That's where the 30 comes from. For the cache line, and I need an array. I'll do that the other way around, right? Include array. I think I'm just going to round up the sieve size to multiples of 30. Otherwise it gets too complex. We can just demand that max value is a multiple of 30. Nah, that's too much. Yeah, what is that? I think we can do the following. I'm going to delete this, right? Because I need a way too large table otherwise. I think the number of That's the compression. 8/30, so 4/15. That's what we had, right? So every 30 integers we have 8 bits in the sieve. So the sieve size is then 8, which is the repeat, times the rounded up value of max value, rounded up to primordial, times primordial. And the way we round this up to primordial is by... Sorry, yeah. Wait a minute. No, divided by primordial. Excuse me. Yeah, so we get 8 divided by 30, and then here max value. But I'm not sure about the exact stuff, so I'm going to round up max value with primordial, which we do by adding primordial minus 1. And then dividing it by primordial, and then multiplying it by primordial. We add primordial and divide it by primordial. That gives you the rounded up value of max value divided by primordial. And then if you multiply by primordial again, you get the rounded up multiple of primordial, of max value. For example, max value equals 30, 300. 300 plus 29 divided by 30 is 10, times 30 is 300. Because it was already divisible by 30. And if we make it a little bit larger, say 301, then we want to round that up, we want to get 11. And we do, because now we get 301 plus 30 minus 1 is 330. Divided by primordial is 11 times primordial is, well, 11 times primordial. Instead of 10 times. So we get 330. And then, of course, the last two drop out. So, blip. That's then the answer. Okay, now we need a conversion between the sieve index and integers. Not const expression, let's put it there. This thing needs a name, let's call it table for now. Static table. Going to make that one private, I think. Actually, nah, yeah, whatever. Like I said, if it's const, might as well make it public. definitely need bitset here as well. It's the number of integers. No, the number of primes. I'm not sure if this int is large enough. Nah, might as well make it an int. So yeah, 0 should give 0. And then every time, no, not 0 should give 0. 1 should give 0. 1 is just not a prime. So people might want to know that. Or do we include 0 as well? Yeah, well, you can pass 0, so maybe 0 is 0. Okay, so 0 is bit is bit 0 here. And then every time we go 30 further, stuff repeats, and we have 8 entries. So I could do like something like n divided by primordial. I think we're gonna need both. Primordial is an int. I feel like using an int here. No, that's not possible and is definitely unsigned. I can divide by an int and then return still this, I suppose. So let's call this ndiv. And mod. There's probably no way around it. We need both. And then we return repeat times ndiv plus table lookup of nmod. and the other way around. Hello, mashallah. This would be true if this is always smaller than repeat, which I'm not sure of. But yeah, it has to be. It has to be. I mean, this is just the right way. Now I have end-div. So you have... how can I get back to that? A different table lookup, I think. Let's call it IDIV for now, because I'm not 100% sure. And well, then we have imod. This is an int as well. Totally. Am I live? No idea. A lot. That would fit into the same cache line. Might as well do that, I suppose. It's not really like that I want this to be a single cache line, but you know, if you read the table, you might as well have the whole table instead of needing to read another cache line. And well, these things are const, so if now you read any table, then you have both tables at once if you put it in the same cache line. So I'm pretty sure that if I do this, then that will be the case. As long as I put them in the .cxx file the same way, in the same way. I don't think I have to do this here. Probably just in the in the CXX file, or I can just do primordial plus repeat and then use an offset in the table for the other one. Let's do that. Premature optimization manually, while it would have been done by the compiler anyway. But hey, I'm from before CPUs had I don't know the name. But they used to crash back then, the whole operating system, when you made an error in your program. So how's that called? Protected memory or something like that. Okay, so this one puts primordial first, and then this one is the table, and then I'll just add primordial to it. I mean, really. Yeah, okay, see you. Now we need to make this work. Mostly that means I need to add that table at the right values. I think that I should put that bit set on the heap, because it might become very large, doesn't fit on the stack. And right here I'm already thinking about putting it on the stack. No, guess it doesn't matter. Oh wait, I was going to do it like that. I'm going to regret that, I feel. It must be a fixed value. Well, before that, compiles on links. Utils. At the very least, I need to define that. Can I do that from my... environment is the question. Sure I can. But I forgot how. What about an export CXX flags? Define primes test code. You can hope. No. You can only hope. But then I have to use CMake to compile this thing. What was it called? Atkin 3. Not to mention that it is using these libraries here, utils and stuff. Atkin 3, I mean the AICXX objects. Oh, let's add warnings to it as well. Atkin 3. Why the hell did that compile? It does define primes test code though. Oh, that's nice. It's totally not what I wanted. Very confused. It wasn't the Atkin 3. No, it is called primes. Oh, that's why it compiled. Maybe I should just use Atkin 3 then to test it. So Atkin 3. I'm going to need primes, so might as well test it gewoon just right here and not in primes itself. Primes, what is utils primes? I need the primes still, let's say 10,000 or something like that. Include, now we need to do include sys.h here because I'm using utils and stuff. Utils, oh no, well, it's currently just called primes. Yep, and then here we have Atkin 3 primes, let's see exact. And this is just nonsense, I suppose. I don't think it should be added here at all, but okay, let's just add it somewhere else so that it's not whining about types. It compiled, unbelievable. Undefined reference. Primes, okay, so now we need to add everything. Hold on, why is this music so loud suddenly? Shitty music anyway. God. Primes, primes. That's the missing constructor. And well, we just know that we're going to have some static stuff to tables. Can we switch here? Oh, I can switch. Unbelievable. So that one, table. I think that's all. Hopefully it says, please don't repeat a line S or something like that. Primordial plus, I think that should work. Primes requires template arguments. Yeah, oh. Why? I'm being stupid. Do I really want to do this? Could make it a base class, but no. Then I cannot even use sieve. Seems silly. Yeah. Fuck. Okay. My mistake. Let's put everything in a header. Because it is a template. Use the undeclared identifier primordial. You have to tell it everything, right? Expected semicolon at the end of declaration. Correct. On it links. Unbelievable. Okay, so now my table is filter zeros, which is of course not what we want. I was working on this, but I need prime numbers. So let's first get the prime numbers working. Comment this out. Okay, so what we want is that if I run over n starting at 0 for a few n's, yeah, I need a lot of them. Let's try 100. And then we print out n and it's a static thing, so it should probably something like that. And to index n. But the only n that we are interested in, no, actually, if yeah, we should never call it for something that doesn't map exactly. So so what I should do is modulo 30 and then just filter out the ones that we do want. And that should be 8 of them. Is that correct? Because it just looks really weird. I would get 1, 2, 3, 4, 5, 6, 7, 8. What about those then? Oh, these are just not, maybe the 5 also not. And this is 8. Those small numbers, let's just go here. Which are the primes here? 1, 2, 3, 4, 5, 6, 7. Did I skip one? One, 2, 3, 4, 5, 6, 7. No, I only see 7. Or is that correct? Anyway, for those numbers, the integer should have incremented exactly. What about, I'm just going to do some ASCII art on this thing. Yeah, the rest is not complete. So yeah, 31 is a prime. Okay, this is not easy. Oh, wait a minute, actually. No, it's not. 91 is not a prime. Or is that not a problem? No, that's not a problem. That cannot be the problem. Okay, I'm going to put some spaces in front of it. Why? P. Oh, capital P. Let's put some stars in front of bigger primes. But 31 is definitely prime, so I want to put a star here. So everything that is a prime must have a star. And then 91 is not a prime, but it's not. That's okay, because well, then my sieve is going to tell it that it's not a prime. So, but I'm not sure about the small prime. So 2, 3, and 5, I'm gonna skip. Just look at this one here. So the next one is 37. Yeah. Where's my vim command for highlight all primes? I say that, but I could actually do that, you know that. Or I could just know from my head what all primes are. 11, 13, 17, 23, 29, 132, okay. And apparently these are, I checked these ones before, they were also 7. So 31, 37, 41, 43, 47, 53, 59, 61. So then we go up here again. 61 is a prime, 67 is a prime, 71, 73, 79. Oh, what? Shocking. I missed a 19. Yeah, 49 is not a prime, but that's the first non-prime that is in the table anyway. That's 7 squared. So, totally happy about that one. 79, 83. We have that one, and 89. Okay, and then we get up here, and I guess those two also work. And now we have 1, 2, 3, 4, 5, 6, 7, 8. Aha, I'm totally happy. Finally, we have 8. Primes, where are we? Remove primes, vi primes.h in tube. I'm calling n to index. That means that I can now figure out what the table should be, and then it becomes so logical that I'm slamming my head in the wall for not just understanding that immediately. I feel so stupid. I am stupid. It's absolutely the case. Because why do I not just know what this table should be? Unbelievable. Okay, let's just pick an n. Next. Pick an n. N is 1. It gives 0, but doesn't. Is that correct? That's probably correct. And a 7 is not correct. Okay, so for n is 7, we should get 1. Going to fill it in. 1, 2, 3, 4, 5, 6, and 7. Yep, that's what we want. So with an input of 7, I want to get 1. Um, 7. 7 divided by 30 is 0, so this is 0. 7 mod 30 is just 7. So the return is repeat times 0 is 0, plus whatever is in the table at position 7. So the table at position 7 must be 1. Is that correct? Yay, that worked. Okay, now we understand how the table works. Just index is a prime, and then we set the next one. So easy peasy. And that was 7. So now we get 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, and that was, and now we have a 30. No, we don't have a 30. Well, actually we do. No, we don't. What? This is index 0, 1, 2, 3, 4, 5, 6, 7. So it's index 29 here. And we have in total primordial 30. So this is the end, and yeah, of course it's the end. 29 is the last one. And then we have another table which has 8 entries. I'm still too stupid to understand what that then is. Or not. Well, that's going to be this table here, index to n. So we just, let's say we have index 1, 0, 1, 0, 1. Those are just the primes. The small primes. 17, 19, 23. I'm missing something. Yeah. What the hell? How can I have 8 entries here and not here? What the hell? Index 7 is 29. 0, 1, 2, 3, 4, 5, 6, 7. That is 29. Can't, it's like sitting in the dark again as usual. Okay, 29, 28, 27, 26, 25, 24, 23. I really don't see what I'm missing, sorry. 24, 20, what was it? 23, 22, 21, 20, 19. That's 5. 19, so that one is 17, yeah, of course, 17. 16, 15, 14, 13. 12, 11. 11, 10, 9, 8, 7. 6, 5, 4, 3, 2, 1. I guess I just forgot that 1 was a prime number. Make. Well, this should work. 7, 11, 13, 17, 19, 23. So 31 is 8. And then 37 is 9. 41 is 10. 43 is 11. 47, 49, okay. 53, 59, 16, 17, 18. I guess it works. I'm going to do a modulo 30 test. I have to need that as well. So 1 is in the sieve. Can you still not enter binary numbers? I think you might be able to. One might be able to. C++ 20 maybe? I don't know. Let me enter binary number. What the hell is this? Maintenance, dude. We don't have caches anymore. 0B maybe. Yeah, apparently. Well, let's try that. 0B. Yeah, that wasn't useful. What I want to do is edit Atkin 3. Let's see, Atkin 3, and then just skip all numbers that are not in the sieve. Dude. Locality is not working. I'm missing a +1 apparently. Well, that looks good, doesn't it? Looks so good that we can go to 200. Pretty sure that worked. Now, next step, the other function. So once we have this, we have an index. And then, of course, we must have that map to... What am I doing? Might as well do this. Map that back to whatever. I'm gonna replace this with a type, some type. This is index to n then. Index to n. Index. No, might as well assert. No, that seemed to work. It seems to work. So we go back, we can go back and forward now. A minute, how was that compiled? That's without assert. Well, I looked at it manually and it works, but there's no assert, so we should of course fix that. PI print environment, I mean. Let's run it in debug mode. So there was an assertion. Assertion and 2 equals 2 failed. What? Yeah, okay. Thank you very much. The output was correct. Yeah, totally. Okay, so What is next? Next, we can implement is prime. Yeah, it must be in the sieve, otherwise it's not prime. And then, well, except actually when it is 2, 3, 2, 3, or 5. Yeah. Okay, so 2, 3, and 5 are not in the sieve, but they are prime. And if they otherwise, if they are in the sieve, then we can convert that end to an index. Then it is convertible. And then I still have to test if this prime by testing the bit in the corresponding bit in the sieve. That should totally work. Provided the sieve was filled, of course. And I might as well implement reset and next prime. Yeah. No, I'm not happy that I use standard bitset. I don't know if bitset has a fast way to find the next bit that is being set. Otherwise, I can just use my own bitset, since I'm using utils anyway. Let's have a look at that. Why do I have the horrible feeling that right now I'm just, you know, opbiechten in English. I was looking at this and I just really seriously have the feeling that my bit set is faster than standard bit set. What kind of arrogant feeling is that? I was contemplating, well, maybe I should look at the manual, the documentation of bit set, if it has a search next set bit. And then I thought, yeah, but my bit set is faster anyway. What? Let's look it up. Testle any non-count size, set, reset, restrain, too long, operators, hash, no search whatsoever. Okay, let's have a look at my bit set. Iterator, right? I need example code, but I'm sure I can, yeah, next bit in, that's what we look for. I'm sure you can iterate over bits that are being set. And that's fast. Extraordinary fast. So, well, I'm gonna use this one, I think. Though I don't seem to have any documentation for it. You could probably find code that is using this, that iterates over bits. Let me steal that. So this is dynamic as well or not? How many bits do we have set here? Or is this bit, this is not a bit set that can be larger than 64 bits. That wouldn't help. Oh, right, yeah. That's just for a single type. Type T. That's not what I was looking for. Yep, not working. Sorry, this is the wrong bit set. I don't have another one. Definitely have another one. I think I have let's go do different window. I have one in lib ECC, I'm pretty sure. bit set. Old code. Still type the void. Yeah, this works. Bit set index. So then that means we can scan, right? Hopefully. Oh, not 100% sure though. I do have documentation for this though. Select the bit up left. Move one bit left in the bit set. No, I want to find the next bits. Move n bits left. Move n bits right. Bit set index iterator. So maybe also only one bit and increment, decrement. Find one. I think we found it. Find one forward, find one backward, find one. Okay. So maybe it does have it. Let's find one. This is old code. It even uses register, which isn't a keyword anymore, or reserved, I think. So I'm not allowed to use it. That's slow. It's just searches or shift mask one bit at a time, looking for the bit that is set. Yeah, I don't like that. So it's not really super fast. See, now I'm at that age that I think I'm not going to write this again. I mean, decades ago, I would, and as you can see, I did think, well, then I'm writing my own bitset. And then decades later, it turns out that, oh, this does have a search for the next most significant bit set. So it does use assembly instructions that search for bits. I even wrote it in assembly. Oh, there's my. Oh, that's the reason. It's if def i3. This is for 32-bit. So for 64-bit, it might actually be fast. If we just use find. Let's see. So the opposite. I wrote it in assembly for a 32-bit CPU. And it's calling the slow find one forward and backwards for 64 bits. Because I guess I wrote this when I didn't have 64-bit yet myself or something like that. Code is too old then. Dang. I hate a bit rot. By the time I die and then 10 years after that, none of my code is interesting anymore. Why do I even write this? It's all evaporating in the end. And now I can look on the internet, like search for, I don't know, someone who wrote the bit set with a search the next set bit in it. But then you don't know if they went all the way, or if they really wrote something fast, or that they just made something that works. I already have that. I'm just not happy with how slow it looks. It should be possible to access the underlying array of a standard bit set. Why wouldn't it be? Nope. It is not revealing that information. Well, normally bit sets can become quite complex, but we don't really need much, right? We only need to be able to set a bit, test it, and flip it. And yeah, that's it, I think. One bit at a time. Compressed bit set library. That sounds interesting. Bit set search function. Yeah. Blah, blah, my eyes. I think I'll just use the standard bit set for now, just because you have to make some progress. In which case, reset just means setting the an index to 0, I guess. I'm using this type all the time for index. Yeah, and now we must find the next index that is set. But index 0 corresponds to 1. I'm not even sure anymore. 0 actually, index 0 should correspond to 7, right? Or No, I forgot again. Really. So this is index 0. So everything is 0. So we just get the S table primordial plus imod 0 to the first entry of S table. Well, the primordial index. That is 1. Yeah, and that's not a prime. So index 0 is 1. So we want to start with 7. I guess we need a bootstrap as well. Okay, that sucks. Let's just use negative values. But then, yeah, why not? So 0 is 5, say. Minus 1 is 3, minus 2 is... I'm setting it to minus 3. And are we looking for the next value? Pom, 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 ba-dum, pom, pom. It's kind of nonsense to do that, I guess. But it's kind of good for documentation as well. Sometimes index is less than 1. It's a special case then, right? I might as well return immediately. No P needed. Well, once we found the next index, I can return index to n of the index. Okay, if the bit for that index is not set, it's not a prime, so we go to the next one. And this I consider slow. So it's all, you know, well, relative, I guess. Hello, Peter. Then all that is left now to finish this is to implement the constructor, which should initialize the sieve. Oh wait, I wanted to make this dynamic. So I'll make this dynamic. Might as well not use standard bit set if you ask me. But okay, let's say that's for the future. I'll make this a pointer, sieve underscore. What was the bloody order? Index second. New the bit set type. Bit set something. That was max value. No, it's not max value. It was sieve size. Comma index, and I might as well reset it. -3. U int, not on it. Did I type on it? No, I didn't type on it. On it. I did not type unit. You mean uint. Uint 64. It's an unsigned integer of 64 bits. It's standard type. So I think that default constructed bit set is a bit set with only zeros, which means that absolutely nothing is a prime. We can test it, I guess. VI. Actually, I still need to throw something. If we try to call next prime and there is no next prime. Oh, that sucks. Would have to test that here. Even. You have to be getting me right. Slow, slow, slowest. I don't know. Exception. Like, we could have guessed that. Standard out of range. I'll just look it up. I really clicked on it twice and nothing happens. Tja. Okay, now we throw something, but I want also now to print them, right? So that worked. So I'm just going to have a loop. It standard out primes next prime. Let's just do that, I guess. And that then should throw an exception. Out of range out of 5. Great, that worked. No, we cannot go around it anymore. We really have to implement this bloody thing here. fill the sieve. Now, since I'm allocating this on the heap, meaning the bit set can become so large it just doesn't fit on the stack. So I want to put it on the heap. Might as well allocate an array on the heap and implement my own bit set, if you ask me. Or I could use a vector of 64-bit ints and then wrap my own bit set around it. Because then I can pass that to another file. Well, even better. I mean, then I don't have a template anymore. The amount of code that we need for this is huge. I really don't want to have that depending on the template parameter. It's just silly. No, it should be dynamic. So could replace it with a bool, a vector bool, for a start, I guess. But okay, no, but let's just do that. So I want to get rid of standard bit set and make it dynamic. So use a vector of bools. Which is overloaded, by the way, to actually use 1 bit per boolean. And then of course you can we don't need to have a pointer there. So then we just allocate it with the sieve size as the size, where then the sieve size must be calculated actually from the max value, which we don't have to pass to pass the thing, not the template. And this has to go to the .cxx file then, as does this. Let me first remove the templates thing. Okay, I have to turn on the lights again for that special key, or not. Sieve size, max value, blah blah blah, that seems to work. I could make it a const expression. Yeah, why not? You know, I mean, basically it would work as a const expression as well. For that matter. It's public, so maybe someone wants to use it as a const expression. You never know. And this is also a const expression, and the very static kind of gives it away. Const expression kind of means we allow you to use it in a const expression, which then doesn't work if this isn't a const expression. And I feel that it is just really silly to do that, so I'm going to remove these const expressions again. Because the table isn't a const expression. I think this should work. Except, of course, now we don't have a test. Test. So just test. What the fuck, man? 1G. Mask. The vector. We have a test and we have a test, and that's it. Oh yeah, sieve size. Do I have a sieve size now function? Yeah, we have a sieve size function. Oh. Yeah, but it just becomes the sieve size. And here we have then the sieve size function, or function of a max value. And then we need to fix a test. So a test becomes then just that boolean at that index. Here's the other test. No. And then we can move that to primes.cxx, because now it's not a template anymore. Move that is. Let's steal these as well. Prime.h. I'm typing all of this in the complete darkness. Well, I'm not looking at my keyboard anyway. So I'm not unhappy about finding the hashtag here and the double quotes without problems. Include prime.h. So at the moment you start to think about it, it goes wrong. It's usually. Yeah. Let's set 1 bit. Which index? I think that index 1 that represents should represent 7. So no. I should have. Let's see that all believe this thing. Atkin, this thing. Prime.cxx. Primes.cxx. Nope, it's primes. Primes. Unused max value. I guess you have to do that, right? Let's just store it. Max value. Max value, and then Store that as well. Yeah, where's my TXX file? So no, I just have to store max value here. And no, that went wrong. Can't find the comma now, of course. Max value. Warning, comparison of entities of different signs. Oh, really? And the same warning. Yeah, index is, okay, let's make this an unsigned then as well. Int 60, primes, error, definition of primes does not match any declaration. So, I forgot to update that one. Primes, the declaration takes now the max value. And I have the feeling that I also have to update Atkin 3. Because this thing now needs to use that, yep. And this is just that type. Yay, it compiled. Now let's see if we throw at 5 or at 7. Atkin 3. 7, we have a 7. That works. Now there's a lot of where that came from. The whole bloody thing is just prime. Everything should be set. Amazing. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. Great. Okay, now let's do this. I have to... let's just use this, right? Fast prime 7 is dynamic, isn't it? Totally, it is dynamic. I have to adjust it though. And I don't want code duplication. So if I'm going to move this to the other file, then we don't have fast prime 7 anymore. It's just how it is. I think I'll just copy this and then change it, update it. I think then that this function here, calculate prime, should become simply a primes member function. Let me see. Start. What all do I need? Probably everything. Why not? Yeah, this also, but I can put that in. Maybe I should put all of this in an anonymous namespace, not in the class. On the other hand, I have been using these two, kind of. Prime index type, what is that used for? It's just a literally the index, so in so many index prime. That's impossible because I had 5 billion primes. Didn't I? Yeah. No, 5 billion. Okay, now I'm confused. Yeah, I did this. How is that possible then? Oh, because I didn't. I had to comment out code that stores it in a vector. So I didn't use the prime index at those values. It just won't fit in your memory anyway. If you have more than 4 billion of 2 to the power 32 primes, then you run out of memory. Typically. But we would not run out of memory in this case. Ha ha. Because now we do it differently. So yeah. That has to be larger or not used. You see how good it is that I made a type def for it. Imagine that all of these cases were ints. Just saying int here. You would not know what to do, really. You would it would be so confusing. Every type should be its own, has its own name. Well, primordial. I only need to calculate primordial for small integers. That is true. And for the repeat, idem, same thing for the repeat. So yeah. Oh, and that's the only place where we use it. Okay, that can be an int. That can be an int. Yeah, and these two can be stay at that. Although the integer can also be negative. That's interesting. It's literally also what I was using. So maybe I should move these two primes. And then use that as well in the code that I just wrote. I mean, I am including primes. No, not yet. I'm going to move everything here from that file to the other file. Meaning, plus primes 7 is no more. I'm going to copy that to primes.cxx mostly. It's sometimes to primes.h, but okay, we can just switch. So for a start, these two are going to be added to the class, So to dd, next, switch to the header file and add them here. And then of course have a good look at everywhere where I use this, if that can't be prime type. Well, maxval, no. Is in sieve. It's just a random integer n, so it's not really. Integer n to index. It's also random n. It's not really, not guaranteed a prime, right? So, no, that definitely also not. Max value is not primes. Max value again is prime. It's not prime yet. Next prime is a prime. This returns a prime type. And that's it. And then I have a lot of them that are basically just positive integers. Don't have a type for that because I have a negative integer type. Let's make a new type for those. How shall we call that? N type. It is integer type really, but it is a positive integers. Why the hell am I using this? Am I using it at all? Only for index and only because I am abusing the thing there. So we could do, I could introduce an index type, I guess. But but then integer type. Okay, I have to go to the other file. Integer type is being used for these things can be negative. This can become negative. That's annoying because of the minus sign here. So maybe I should just use not integer here, and then use integer for unsigned integers. Or maybe just forget about the unsigned integers and use signed integers everywhere. 64 bits, 63 bits is large enough for everything. It just feels silly sometimes, you know. If you're 100% sure that it's a positive integer, a non-negative integer, then it just feels stupid to use a signed integer. That's a real problem here. Calculate upper bound. See, all these things are positive things. That's the reason why I use an unsigned int, but it's really not a good reason. What does n has to be for this log to be at least 4? It's e to the power 4. Okay, we'll be right back. There will be light. E to the power 4. It's still not enough light for my calculator. There it is. Shift. What? And that takes care of negative values of n. And this is internal, so who cares what the type is? Nobody's gonna have more than 2 to the power 63 rows. During my lifetime anyway. And we know what happens to my code after that. Even the sieve size is not that big, because nobody has that much memory. And this should be signed. Oh wait, it is signed. Yeah. What the hell? What happens? I'm trying to get rid of one of the 64-bit types. I think everything should be signed. Integer must be signed, is signed. I'm just going to get rid of all the unsigned 64-bit types, unless it's being used here, because why wouldn't I? Just keep that. Yeah. I really can't expose this to the user and then ask for an assigned integer. Calculate prime still -3. It just feels stupid. I think computers have to be redesigned from scratch, because this is a serious flaw. Oh wait, this becomes internal. Maha, it becomes internal. So I can use the integer here. Integer type, yeah, well basically I can use integer type for everything. Why wouldn't we? I'm not going to do that though. It feels a bit too drastic. Difficult decisions. It's about the only place where I need something that is negative. This is positive, positive, positive. Yep. And then of course all the uints as well. So what now if I do substitute all uints? Well, maybe it's still drastic as well. Let's first look at them. Upper bound. Okay, that would be integer type as well. Integer in, integer out. Calculate primes for the max value. And now we can just make that a large integer. So integer stands for large positive integer. Upper bound, well, that was literally returning integer now. Cycles, that's something else. Pi. Must be 64-bit, yeah. Why not unsigned? It's hardly integer. It's an index. Let's keep uint. Cost is required then. Question is an int, I think. Square root. Max value. Okay, let's just make that an integer again then. See word. First row with okay. It's not an integer, it's also an index, isn't it? So row, index, same thing. I could make a prime number index type, I guess. But yeah. And then we are around. Okay, let's keep it like that. Let's write that. So it becomes integer type. And now this is unsigned. And then I can use integer here. And here. Into index. Okay, well, let's use also here uint for index, although could make an index type, I suppose. Okay. And everything was moved to namespace utils, so we have to put everything here in utils. Well, maybe not the main, which I'm going to remove completely. Well, then again, yeah, why not? Okay, that is anonymous namespace. Till here, I guess. And then this must become a member of primes. But it's not going to return anything anymore. So I don't have a result. But for now, let's just keep it. We don't return anything, however. So I need to put this in. It's a private function, I think. Probably. Private function. Let's put private functions down below. Mm-hmm. Mm-hmm. Yeah, I don't know, man. I don't know. Maybe I should test. Let's try to compile it for a start. So move all this code. Oh, I know I'm going to need a few of these as well. Tuple. I'll put everything here. Array, C standard lib, already have. Moth, probably. With C standard lib, I don't have C standard lib. I don't know which one I need. Let's just include nothing and see which one I need. So I'm going to copy all of this. Put that all here. And then this thing, calculate primes, a private number, what private function, I just call that from the constructor. And that then must go, and maybe I should just make it a constructor, but yeah, probably it's just is a constructor. Okay, forget it. This whole thing is just a constructor. I'm using it Atkin. Oh, it's just testing. It's just okay, whatever. It's primes now. Yeah. Where does this sieve size come from? There. That's a different sieve size. Oh, I have two sieve size. I have two sieves. So I'm having two sieve size. Very annoying. Very annoying. And confusing, I guess. Let's rename the other sieve size to something. What about final sieve? But the warning doesn't go away, of course. Yeah, I changed sieve size to an unsigned now. So you get this, and that's what you get for making unsigned types, using unsigned integers, which is just stupid. Never use unsigned integers. Yeah, I guess I can make it unsigned. Normally I just cast it to signed, but in this case I'll make an exception and use unsigned here because it is an index and I'm not using negative values. That's the only place. No way. Less than sieve size. There's another. Signed. Hey, Post Bunny. I didn't eat yet. I finally started feeling it that I didn't. Stupid stomach, just complaining. And then we get that. Oh, it's just way too. It's just way too small, dude. You don't think that you can do that. You gotta ask for at least a billion primes. A billion primes, up till a billion. The smaller is not even possible at the moment. Okay, that takes way too long. And this is interesting because the whole sieve is 0. Is it? I thought I said a few bits. Did I remove that? No, of course I removed it. I removed it because I replaced this whole thing. So now I don't have a result anymore. Result resize, we're not going to do that then. Upper bound, I don't need an upper bound anymore. Wow. Sad. Okay, no upper bounds. We don't time that anymore. I don't need a prime index either anymore then. Not really. Don't think so. Sieve. N to index prime is true. The new store to store a new prime. So we're going to delete this and then we don't have a PI anymore. Let's just put PI here, who cares? Let's just make an int PI. Oh, I want to test debug primes. Then I have to. Then I need a PI. Well, that's some debug stuff. Super annoying. Regret that I have made PI so short that I cannot grab it. Never use abbreviations. There's another PI, see? Every time these two lines just belong together. So we have those a few times. There's another one. On here it becomes too large. And again. And then a test, which you can't do anymore because you don't have an upper bound. Yeah, test enough. Let's remove that. We don't have results. I do need to convert my sieve though before freeing it to the other sieve. No, I already failed it. Bullshit. You can just delete it. It's not that many PIs, I have to say. Okay, so looking for PI works, but then not entirely. I needed this here, this line. I don't believe it, but since it's debug only, I might as well increment it here. Ew, it's now debug thing. I'm going to rename PI to debug PI, I think, because, well, clearly it is. Okay. Debug PI. And then increment it. Yeah, no more results. So different results. This might even work. Unused to calc upper bound. Yeah. Let's make it a member function. Just because. also static. Ah, looks like prime numbers. Need debugging. It takes a long time, but let's keep the debugging on for now until I see a lot more. Let's print 1,000, 10,000, 1,000. That's just going to work. Why am I even doing this? Let's check that 25 and, well, 25 and 49 is not in there, and then I'm happy. And then of course it printed so much that we have to write it to a file. Or, yeah, well, okay, VI top. 2, 3, 5, 7, 11, 13, 17, 19, yep. Perfect. Okay, so let's print the first 100,000 primes. And at least then I can test it. I'm just going to print it like that. A 100,000. So that is the 100,000th prime. There are 100,000 primes less than or equal. So that is exactly correct. So all of them were prime numbers, and we didn't miss one, didn't print extra ones. Well, pretty sure that works. Now, even better, I can, let's switch to release mode. Source, configure. So this should finish in very small, very fast. What is this? New vector in primes.h. I have an array. Don't have a vector. I don't have a bit set. Oh, I replaced the bit set with a vector. Vector. Now we don't have mem sets. That is C string. Make. And don't have garbit. Where the hell is garbit defined? So these are the missing headers. Garbage, anyone? New? C limits? One of these three. I don't know, what is in C standard lib? I don't think it is new. No. I keep entering that. What about, it's probably C limits. So this should also not compile them. Nope. What about the last one that I didn't try yet? Of course, the last one. That even compiles. So the other ones are not necessary anymore. What? That's kind of strange. Why did I use new? Can't remember it. I really have no idea. I have no idea. Limits. I would use limits for numeric limits, which I'm not using apparently anymore. That worked. And yeah, now I would like to test really big things, like things that just take too long to compile, to run. Let's begin with trying to print the last prime. How do I figure out the last prime without printing it? It's not really possible, is it? I mean, I have to just do this call and then remember the last prime. One, two, three. About two more. No, then I get this many primes, which is not going to work. Let's add a 0 here, that would work. So I'm going to do prime type. Actually, primes, prime type. Last prime. And then here we do last prime is next prime. And we just print last prime. Bad alloc. Oh, that should not happen. Should definitely not happen. Something is wrong here. Yeah, that's okay. Yeah, no, I don't have that much memory. That's correct. But why is it that big? The final sieve size returns absolutely ridiculous value. Negative value. Aha! Aha! Don't tell me I returned an int here. Quit, yes, vi. Primes. H. Fine, yeah, return int. Stupid. I think that is better. Don't have other silly ints. It takes too long in debug mode, so now I have to go back to release. We don't have that many primes, really? Yeah, and what was being thrown? Standard out of range. Catch the thing and ignore it. As that's correct. So if I is 0 and then we do this and it succeeds, then we assign 2 to last prime and then we continue and we increment it. So now I is 1 and last prime is the first prime. So it works. And then at some point it fails, these two match like that. And the fact is prime index. Okay, that is shocking. Oh no, it's not. I do a break so it prints something. Okay, we have only 455 million. And I was trying to go 1 billion, so that's a bit too much. And this is correct, I think. Yeah, 6, 7. Cool. So this is also almost 10 billion. Yep. Now I would like to make it even larger, but then it's going to take a bit too long. But yeah, I have to eat as well, so I might as well run. So just initialize even more, and then just run until whatever. Just run until we run out of it, and then it prints it. And we don't have to print this anymore. Maybe the break is nonsense. Could do a return here. So this is 1, 2, 3, 1, 2, 3, 1, 2, 3, yeah, 100 billion. I definitely want it to work for 10 more, and then I'm happy. But it takes so long. So to run this to see if this works. I'm not sure if I tested 100 billion before. I'm just going to run it. Oh, what is this? Result of comparison of constant with expression type int is always true. Yeah, now it's becoming like seriously big. I'll make this also on that type. Thank you, compiler. We would have waited for nothing. Or not. No, I didn't want to. That was actually didn't even matter. Exiting the loop because of the exception. Wait, let me start it again. I want to know how long I have waited, or should I wait it, or will have to wait the next time. Memory, it's almost using no memory. I mean, less than 10 gigabyte, I would say. Can we calculate how much it should be using? The sieve that I have allocated, I'm allocating 2 sieves, but okay, 1 sieve is larger. Oh, I have to calculate 2 sieves then. That's a bit much, too much work. Nah, still. We go up till 100 billion. Do this one. That's 4 billion primes. It's almost a real test. So number of primes gets larger than 2 to the power 32. But our sieve is smaller than this, namely, well, I can look at the code for that. Prime cd primes again, and then we look at the primes h, and then we look at function final sieve size. max value, and I'll add it here. 41180548113. Yep. A plus, as if that matters, 29 is that. And then divided by 30 times 8. What the hell? Oh, that's the number of bits, yeah. We have to pass the number of bits to the size of standard bool. So this is in bits, so divided by 8 is bytes. I'll just turn off this light. Oh, I don't know. That's 137 million. 137,268,494.7. Where's nothing? Well, nothing. 137 megabytes. Megabytes. The other sieve is even smaller, I think. Just a little bit smaller. Good. Then together they're like much less than 1 gigabyte. Okay. Good to eat something. finish? No. Oh, is that correct? That's bloody correct. Yep. No, it works. It's only 5 minutes. Well, I want to do the what is it? I want to do the big one as well, but that's gonna take more than an hour. Oh, guess I'll do that while I'm going to bed. When I'm going to sleep. If I'm going to. Oh well. Later. So. What I want to do small thing. Nah, a million is a bit too small maybe. $10 million. $10 million. Yeah, it's got a core dumper, right? It's not core dumping. What the hell? I'm confused. thought that was so not enough. Yep, it's correct. Well, I can wait 23 milliseconds every time, so maybe, yeah, it's okay, good enough. That let's see if 1 million works. How low can we go? Jesus, even that works. Million. Bah. I don't know what happened to my lower limit or upper limit, lower limit, right? 99991. Mm-hmm. No, there's no lower limit anymore. It finished. I don't understand. It's definitely a limit. 1,000 then. At some point it should not work anymore. It still works. It's impossible. Put the microphone here, make my sound. Oh no, not finished. I'm still eating. Nah. Sorry. I think this is the assert that failed. But I have asserts turned off. So apparently this assert is not necessary. Yeah, this assert requires a minimum of 1 billion. If the compression is 6. But apparently it's not necessary. So let's start with commenting it out. So no longer required. So what I'm going to do now is run this automatically to find if there is a lower limit. So what we do is first we make all generate all primes, I guess, so I can check it up till 1 billion. 1, 2, 3, 1, 2, 3, 1, 2, 3. Because this one works. What am I doing? Coughing. That works right. Right, and then here we do again next prime. That's not going to work. Let's put this in its own scope. And then this sieve is also being destructed again, or you leave the scope. And then here I'm making a new primes with something smaller, which we don't test. I don't know, at least it should compile. Suing using prime type is that primes prime type. Push back in utils primes. No, let's call it gen or generator. In debug mode, I guess. Takes very long. Yep, we are in debug mode. Right, in that case, we have all the primes, but it takes a bit too long. I'll have to do it once at least, so we one more time then. So I'm going to generate. I'm going to use the primes object to generate 100 million, up till 100 million. Yep, and then we're going to test if every prime that we get equals, well, actual next prime. So I'm doing assert last prime equals ether plus plus. Yep, is that correct? I think so. Hello, Kubilay. So another 25 seconds. Yeah, I didn't assert. So that should have worked. No, this is C++, not Python. Okay, so apparently when I do this, then I get all primes up till 100 million. Because I know that that one works, and the assert didn't fire. And I'm so paranoid that I really want to see that fail. Am I going to really wait? I mean, I don't know. This is maximum paranoid. Going to wait another 25 seconds. And then we have all the, then we know for sure that it works. Yeah, now it caught him. So that assert worked. It did not fire. In other words, it works if we just generate till that. And now we are 10 times as fast. So even in debug mode, that you can wait for that. And now we can do the same thing here. I'm just going to go 10 times smaller. And then see if that works as well. seems to work. And I'm going even 10 times smaller, I think, because, well, otherwise it still is too much. 1, 2, 3, 1, 2, 3. This is 1 million. That also worked. 10 times smaller. Now we know it so fast that might as well add a loop for int m. No, it's using unsigned thing there, so as the way I have to pass it. Type that I have to pass. We start with that. M larger than 0. Let's not be a complete jerk. Minus minus m. It's pretty jerky already, but okay. Pass m. And then test if that works for that, those things are primes. If it now fails, I want to know why and where, not just assert. What the hell? Oh, I'm doing return. Yeah, okay, let's use a break then now. And then we break out of this loop and then we just do the next one. Okay, that's better. Hey, but failure. No, it's not good. I don't like this at all. But well, okay, I mean, it's kind of the reason for the assert, then I guess. But it's really weird, isn't it? I think I should print M for every line, because this is not really making that much sense to me. Failure for M. Oh, I am printing M. What? No, this line. Just print M, I guess. So M is the maximum value. We want to generate all primes here. All primes up till and including M. And if that works, then of course every prime that we get should be equal to the actual prime. The actual next prime. So there we still find it, and if you go below that, yeah, it's just the next prime below this one, I guess. And again, so that seems to work pretty well. Well, then here we get a failure. Or not. No, wait. Sorry, but very confusing. No, this is peculiar. It just keeps working, except for those two values up there. Yeah. Plus, it's rather slow, I have to say. Maybe I should run this with optimization. No, it takes too long. Let me try the following. Not printing that. These numbers should always be less than or equal to that number. And then if that works, then I guess I don't have to print it. That was a lot faster. Or exit, huh? Return primed is too large. Okay. Maybe we should not exit. Let's not exit. So it does fail, but only around that particular point. Core dumped even. Okay, I definitely want to test this for a larger M, because at some point I don't want to see any failures anymore. And I want to know what that point is. Why the hell are we core dumping? Loss of wood is negative. Wood index. That's probably no. Cannot go lower than 222 apparently. Then we crash. But why exactly? What's to do with the compression, I guess. But. The compression is at 4. We'll make this 3. Then I guess we can go even smaller. I think. Compatible types on dwarf stack. Now I have seen everything. But yes, M is small. Or the two past. Yeah, so with full compression I might actually not be able to go below 30,000 or something like that then. Try that. For a start. Yep. We're doing naughty things. I think M has to be at least the compression, or what is it? The repeat. More or less, I guess. Is that another literally the assert that I removed? I'm a bit confused here. That is 16 more than the primordial, which is 30,030. Where does that 16 comes from then? Plus it. Oh, it's one less than the. It's one less than the first prime of the second row, which is 30,047. Which I think is exactly the assert removed, if you ask me. It wasn't completely idiot that I added that assert. However, let's look at it again. This one. Oh, right. I'm looking at the square root here. But apparently it works all the way up till max value. So max value must be that. Or maybe this must be, the square root must be larger than the square root of that. If you get what I mean. No, max value is known way sooner. Circle roots. Interesting. I think that's gonna be 1 circle root. What to do? Under the add assert, wherever we add max value into the mix, which is, I guess it's simply the top of my it's the constructor. Nope. Oh, I am compiling without asserts as usual. Do not have something that has asserts. I think bad should have that. I'm not even sure if that works. Resource configure make. This is with maximum optimization and asserts, and debug is not defined. So that's the one that I wanted. No debugging symbols. And still, it doesn't assert. It just segfolds. What the hell? I don't know which one was. So debug. Let's just try debug. Reconfigure. No, resource. Configure and make. Oh yeah, right. So it definitely wasn't had no assert, and that is because I also commented this one out. I want to have optimization and asserts. It should be possible. Of course, that is possible. Okay, we'll just go to slow route then. Now it takes like, I don't know, 14 seconds. Oh, that was not too bad at all actually, but it's still slow. Finally, so now we are really code dumping on that assert that I added. What the hell? Atkin 3. So it must be at least that. And then I hope it just works non-stop. Now I don't know what it is doing because it doesn't print anything. I don't like that. That's slow. Might as well print it. It's so slow that I might as well print it. No, I really need to get more optimization and asserts. How about I just add the C flags again. Export CXX flags. -03. Yeah. I think the beta test actually does have asserts, but the assert macro was still undefined or empty. Actually, no. It should have been replaced with the lowercase assert, which should have worked. What? Is it doing that every time I call it? Talk. Now I know why it is so slow. Oh my god. Yeah, I need a define for that. Seriously. Just so we can turn that off in debug mode. It's not optimization, it's just the debug mode is slow because of it's reading a billion primes from hard disk and then comparing with that. What are you saying, Boys Bunny? What are you saying? Explain it. Check primes. Okay, so I want to look at debug primes. What do we have? So this is always defined is CW debug is defined. Then we might as well do that. Ja, dat is het zelfs. Check prime. Still dramatically slow. Should get 1,000 of these per second. Why is this so slow? I don't get why this is so slow. Really impossible. Should like take 1 or 2 milliseconds for each of these things. It's more like 10 per second that I get. It's 100 milliseconds. I don't get it. I don't get it. Okay, let's just step way more. No. Oh. Why is this so slow? Don't tell me it spends all time here. Oh, it would be horrible. Oh, okay. Anyway, yeah, well, I believe this is the minimum input. 30,047. I'm Mohammed. The good luck means you are leaving. It's kind of strange. Why would 65 have one solution. I mean, that should just never happen. Oh, it's not square free. That's the reason. Yeah. It's only a prime if it's square free. So 65 divided by, well, 5 clearly. Oh, it is square free. That's 5 times 13. What am I missing? What the hell am I missing here? This doesn't make any sense. Modulo looks a lot different. Modulo 12, 1 or 5? Well, if that's the algorithm, then let's use that, although it's not what the article said, or the paper said. Assert. It was 65 mod 12. Is 5. So that is actually correct. This holds for 65. What limit do I need? Okay, I want to run this, but I don't want to write it to disk. And I want to do this for much less than this size here. Reserve, well, we'll just do we pushbacks? Primes reserve, wait, that's primes, it's all the way down there. Yeah, I might as well rely on the pushback here, so let's not reserve this. And then the limit, I'm going to set the limit to, I don't know, 100,000, 1,000, 65 is nothing. Set it to 1,000. That should work in the sense that it should generate all primes up till 1,000. Let's test if that works. So this returns that. I just want to print it. Standard cout P 4 auto P and primes. Okay, and I did not think that 65 is a prime. Now the question is, why is it not thinking that 65 is a prime? Because I would say we get exactly once here. 4 in is 65. We get there twice. Okay, now I'm curious. I'm also happy, I must say, but we get over A and B. Two 7 and 4 1. I do find the 2 7. I'm not finding the 4 1. Oh, what? No, wait. Okay, I'm not finding the 4 1, so it's a bug in my program. Atkin 3.cxx. So the 4 1 means 4 is squared 16 times 4. 64 plus 1 is 65. Yep. And why am I not finding 4 1? X is 4. That should be found. Maybe my limit is wrong. I guess I can just step into it. Looks good. It looks good, but it isn't. Okay, so let's do this in the debugger. TDP main run. Next. That's the wrong thing. Sorry. I meant Atkin 3. Did it even compile that? Didn't. Pre-compiled Atkin. How the hell do you get there? Let's compile to optimization. I definitely do not want that at the moment. Two. I mean, the solution was 4. 4 and 1. So what's my limit 2? Dividing it by 4? Dividing it by 4 here. Oh, what? Yeah, I should divide inside. It's n minus 1 divided by 4 and then the square root. That makes it twice as big, which makes it 4. We found the bug. The limit is indeed wrong. Just n minus 1, then divided by 4 and then the square root. Stupid. This one is n minus 4x squared and then the square root. So that's one is good. Now we find both. Very good. So now I'm gonna run this again from, what was it? I think just 1. Core dump. No. Okay, I guess that if we do this one, then it's like guaranteed not square free. Because it's like literally square. So it doesn't make sense to test it. But let's test it anyway, because, well, this is an optimization. It should still work for It should work for n is 1 plus 4 times an integer, which is what this loop is doing. Yeah, and then the result of that is that then we get an odd number of solutions for something that is not a prime, but it's also not square free. This is 5 squared, so it's allowed that it's not a prime as long as it has squared primes in it, prime factors with a exponent larger than 1. How do I test that in? I'll just have to factorize it, I guess, to check it. Routine Alice. Quite late, I'm afraid. I think I was 30, maybe 29 or late 20s. It was way before the C++ standard existed anyway, so it was a bit flaky language. Not even being standardized, but well, I was only coding on the GNU compiler anyway. Yeah, I need a function to test if something is square free, which means I just need a factorization. We need a factorization. I'm gonna put this here for everyone to use. Nah, this is prime type. Prime type. And this is just that prime to that power. And then I want to return all the primes that are part of the n. And in order to speed that up, I think I'm just going to store all the primes in a vector because I'm lazy. Standard vector prime type. I should probably make this a supportive function of primes. I mean, it's probably going to happen more often than I just want to say, hey dude, put everything in a vector for me. Yeah, let's do that. Okay, so then we have here primes dot make vector. And then I'll move that to vector. To primes, I mean. Make vector. Reserve something. Reset, dry, forever. I think I want to have to exactly till that thing. Range, okay, then we are done. Push back, generator, that's us. Next prime. How about that? We have a vector, reserve it with the correct size. You can resize it to the actual size, I guess. No, it's already the correct size. Could turn the capacity down, but the upper value is so exact that it's not really needed. Reset. Get the next prime. Perfect. What's going on? board. Who the hell has that open? This guy. Let's put it below the constructor. Oh, it's not in my buffer. No, it is. Damn it, I forgot what I was doing. Okay, factorize. Shall we do that? Okay, so just run over all primes until square root of n. Or I'd rather use map. Shall we do this instead? Wait a minute. Yeah, map is better. Hello, Epic Coding. So for a prime, if n is divisible by that prime, then increment the exponent of that prime. Divide n by that prime and try again until it cannot be divided anymore by that prime. And then we continue with the next prime until, of course, n becomes 1. And we might as well stop. If n equals 1, break. We already have a break. Actually, I think I just should do this and not this. Well, if we run into that, something is wrong, right? I mean, what? How would this ever be possible? It's not possible. What could go wrong is that n is not 1 at the moment we leave the loop. Then we just didn't generate enough primes. So we're gonna assert here that n is 1. Okay. Bool is square free integer n auto map is factorize n. We're gonna work with really small numbers here, so I don't care about the CPU. Run over all elements in the map, so it's going to be an int. The exponents. No, not really. It is it's going to be a pair, no matter how you look at it. Prime exponent pair of the map. If square, then square free is false. And we might as well stop. PE, I think this is returns a pair of key data, so that's just second then. Yeah, why not? P second is this int, is the exponent, so if that is larger than 1, then we have a problem. Then it's not square free. Guess I should test that. Deleting Excel, yeah, I would like you to be able to print these things, these maps. That would be nice. Avoid print factorization. Let's just pass the map. PM. Prime exponent map. How cool is that? Yeah, well, no, okay. No, maybe not. How do I print that? To standard hours? Oh, okay. So we need to run over the map again. Let's call this the same thing then. Prime exponent map. Separator prefix. What do you think? I think separators are good thing, name, words. Start with the separator. Print stuff. Set the separator to multiplication. Okay, we print the prime number, which is PE first, should be. Followed by, kind of depends, I guess, on the, if that second is larger than 1, then we want to print it. Otherwise, we don't want to print it. To the power PE second. Yeah, and that should work. So now I'm printing n here, and I might as well immediately continue with the factorization of n. So that equals, oh, like that. No, I don't want to do that. Oh man. I want to do that here, not there. So yeah, now you see 25 is a square. Therefore now we don't assert anymore, even though we have an odd number of solutions. And 29 is, well, not a square, it's just prime even. Odd number of solutions, must be a prime, is a prime, very good. And here we have an odd number of solutions. Well, it's not a prime, but it has a square. And here, for example, 65 does not have a square. It's just 5 times 13, but the number of solutions is equal to 2, which is even. That is also allowed. Two solutions, no square. One solution, prime. And so on and so on and so on. Well, it didn't assert anywhere, so I guess it just works. Let's restrict ourselves to just these. So if this is not true, so if that is unequal 1 and that is and also unequal 5, then we might as well continue, because the result is probably never a prime anyway, or it is always, maybe I should do the opposite then. Let's see why we have to skip those. So yeah, we might as well skip it, because if there's an odd number of solutions, then it is a square. Odd number of solutions, square. Odd number of solutions, square. Odd number of solutions, square. 2 squares even. Odd number of solutions, square. Odd number of solutions, square. Odd number of solutions, square. Odd number, square. So this is just, there is no solution, or it has a square. Well, in the case of an odd number, this one has 2 solutions, but okay, still a square. So if there's any solution at all, it is a square. Like this is no squares, but no solutions either. I'm not sure I understand why that is the case, but apparently that's a speed up that we can do. Could assert this. Let's see, let's check till 1, 2, 3, 1 million, and then I need a lot of primes. How many primes do we have now? Probably not enough. Actually, it should be enough. That many primes again, factorize till a lot. Oh, wait a minute. Suppose that, suppose indeed that we have, that we don't have the last prime. Aha. Yeah, then we're going to assert here. So now we could, if we have, yeah, either n must be 1, or the remaining of the last factor must be, let me think. So a way to check this. Yeah, or the last prime must be larger or equal to square root of n. Then the remaining n is also a prime, so that's no problem then. And if it is 1, then that is not necessarily the case. The last prime must be greater or equal the square root of n. Where the last prime is, well, just the last prime in primes. Just simply, literally the last prime that we have. Primes back. So having this in the assert, we can go up till this squared, which is 10 billion, right? And we only go to a million now. Still record them. Assertion n is less than or equal max value field. I'm checking if this is a prime. Yeah, I don't know. Okay, so in order to be able to do that, I have to still know all the primes up till a million, up till 1 million. So for all these numbers, might as well stop it because I'm just going to replace this with an assert. For all these numbers, it must be true that either this is not true, okay, well, let me think. Yeah. Normally, we're going to skip these numbers. So normally it's either a prime or it is not square free. But because we're going to skip them, we want to make sure that none of them is a prime. So we skip them because none of them is a prime. And then the second assert makes sure that, well, if this is not true, then therefore they are not square free. We don't want to skip primes, so that should hold all the time. Hello, Epic coding. I don't think I want to print everything. Now I think about it. Let's only print the odd solutions. certainly not the ones with 0. It still prints solution 0. What am I doing wrong here? Oh, this. Forgot a line. So it prints only pairs that have odd solutions, and all of them must have a square. So none of these are primes. Letting it run all the way up till 1 million, but we are almost there. Okay, that worked. In other words, because of that, we can skip them. So now we do a continue on exactly those, and then we will assert on this assert. Because obviously we're going to find primes now among the other ones immediately. Okay, whatever. That has to be removed. And then for the remaining ones, yeah, they are either square free or they are primes. I wanted to look at the paper and understand why that is the case. So let's go to the paper. So let n be a square free positive integer with n equals no. So maybe, you know, we just should start here. So what I'm doing now, I'm having an n that is 1 plus 4 times some integer. And we can also continue if that n is not square free, like immediately. So then we fulfill that first line here. So this already, you know, takes care of a lot of stuff. But really, if we just follow that paper line there, we should say if not is square free, continue. Okay. So now you see n is 1 plus a multiple of 4, and it is square free. Square free meaning that if you factorize it, then none of the prime numbers has a exponent larger than 1. Then n is a prime if and only if the number of solutions x, y, with x and y positive, of 4x squared plus y squared is 1 is odd. So what I'm doing, I'm just calculating this for all possible x and y's. And that makes sense, because if you make x too large, then of course, well, then it's never ever going to be a solution anymore. So we know a certain range within that it makes sense to check, and then we test all possible sensible values for x and y, and that way we count all possible solutions that exist. And I'm doing that by running over sensible values of x and the sensible values of y, and then we test if that is indeed equal to n, and if so, increment the number of solutions, and then we say if the number of solutions is odd, then it is a prime. In fact, they say, let's do it like this: odd number of solutions solution modulo 2 is 1, and well, is prime that like that. Assert odd number of solutions equals is prime. Well, okay, let's skip the is prime. Yep, so we have an odd number of solutions if and only if n is a prime. Maybe I should not print this because output is rather big. It's pretty slow, I have to say. You'd think it only has to do roughly 1 million checks. And yeah. Why would my PC take more than a second for that? Whatever it's doing. I'm not even factorizing it anymore. Yeah, by now I'm starting to wonder if my program has a bug, because maybe it's hanging. What the hell? This takes too long. Okay, something is wrong. Something is wrong. What is it doing? Dude, PE. We are purely debugging, right? Debug mode, so I can just run it in the debugger. And runs out. And was going to 1 million, so what, it's making a fast progress there. It is calling factorize. Oh, testing square free. Yeah, we are factorizing actually every integer. N is now, okay, maybe that's what's going slow then. Just takes a long time factorizing all those integers. Yep, unfortunately, then that is the case, I guess. Let's print n then. Just print n. I don't want to print 1 million things. If n there equals 0, print it. Which might never be the case because we skip a lot here. Which is also never the case because it's one mod 4. Although, so I wanted to do every 100. Like, let's say it's mod. Jesus. Let's make it simple. N minus 1. That should work. And that should run up till 1 million. And now suddenly it looks like it's going to be like that very quickly. Oh, it's slowing down. So it's going to slow down till a crawl. Yes, it is. Well, that's the factorization part, I think. Trying to factorize those big numbers, it takes a long time. Still, I don't think I've been this impatient. I've waited longer than this is going to take, eh? Didn't I? Maybe not. I wasn't patient, I guess. I probably stopped it when it was there. And I didn't assert. So, this is correct, this line. But that's a theorem. So we checked it now up till a million for n's up till a million, but we want to understand the proof. And the proof follows. And it says the following proof uses the fact that the unit group zi star, which is, well, that's z adjoined with I, so you just have a two-dimensional grid with all the a plus b i's, where a and b are elements of z. They're also called the Euler integers. And the star takes a unit group of it, and that means that the things that have an inverse. So that's kind of obviously only this. 1 minus 1, I and minus I. The inverse of 1 is 1, the inverse of minus 1 is minus 1, the inverse of I is minus I guess, and the inverse of minus I is I. Meaning that if you multiply the inverse with this thing, then you get 1. Yeah, 1 times 1 is 1, minus 1, the inverse of minus 1 is minus 1, yeah. So these two are their own inverse, and these two are each other's inverse. And no other element of zi has an inverse that, because say 2, yeah, I have to multiply 2 with a half in order to get 1, and nothing. This is just integers, so there's no half in it. So these are the only ones. Yep, so the people left again. I won't repeat it. Okay, so the idea is to find the representatives of Zi for the semi-group. Zi over Zi star. So these 4 here are the this Zi star and the Zi on the Euler integers. And they form a semi-group if you partition all those Euler integers in, well, 4 groups, such that let's say you make 4 sets. You have 4 of these here, so you make 4 sets of Euler integers. And then the demand here is that if you multiply with one of these 4 elements of Zi star, then you get, for every element, you get an element of one of the other sets. For example, and I definitely want to test it out, I think it would be very interesting to try to do this partitioning, even though they don't really use it if you the rest of the proof, which is stops here. Just this is the whole proof, so it's not even that much. But this whole partitioning thing seems very interesting. So now the Euler integers are a plus bi, where I is the imaginary number and a and b are element of z. I don't know how to write that down in ASCII. Well, pick one. So let's say we pick a is 2 and b is 0, also known as 2. And we put that in. Let's make a name for the 4 sets. Let's I don't know, I. It's one set. I contains 1 and more. And then the one that contains -1. Let's call that n. That's n of negative. The I of identity, by the way, but rather random names, I have to say. Yeah, and then I need 2 more for I and minus I, so imaginary. Already used the I. I of identity, did I say that? Yeah. I don't know. Let's call it C. For C of complex? Nah. No. Let me just use, well, let's use C. C and D. C does not stand for complex. C stands for third set. So this one contains I. Oops. And then we have a D, and that contains minus I. So now note that if we take any elements of any of these 4 sets and multiply them by one of these 4 elements, which are the elements of Z I joined with I star, that is the unit, what was it called? The unit group. And the unit group is 1 minus 1 I, minus I. So the idea is now if you take any element of these, and these contain all elements of Zi. Okay, I'll say that here, Zi. Can we write that down? Zi is the set of that, or is it like that? A and B in Z. Something like that, or integers. And I still didn't finish my sentence. So if you take any element of any of these 4 sets, multiplying with one of these 4, then you get an element in one of the other sets. But I only put those 4 in these sets now, and we have to put every element of Zi in it. For example, 2. Well, if I put 2 in here, random place, I could have put 2 in one of the others. Then that means that multiplying it with -1, if I take any element here and I multiply it with -1, I should get the same set. And since 1 is in here and -1 is in here, -2 should also be in here. If I put 2 there, then -2 must be in here. Yeah, because now if you take 1 and you multiply it with -1, you get -1. So we go multiplying it with an element of n, we go from I to n. You could denote that, I guess, with if you take an element of I, you multiply it with an element of I, then you get an element of I. And if you take an element of I and you multiply it with n, then you get an element of n. And if you I is the identity, so this holds for everything. For any element in I multiplied with any element in any set is an element in that same set. That's why it's called a semi-group, because the binary operation here is multiplication, but there's no addition. And semi means that it does not necessarily have an identity. And, well, it doesn't. Well, maybe it does, but I'm not sure. Okay, so we have this, and then we have, of course, that if you multiply n with I, well, it's, how is that called? Commutative. C times I is I. C times n is the same as n times c. It's d. C times c. Well, for every element in C, thus also I, it must hold that we get an element of whatever. So I times I is minus 1, which is an element of n, so this must be an n. And lastly, we have C times D. I times minus I is 1, which is in I, so we have to go to I then. Maybe I should use an arrow instead of... I think an arrow makes more sense. Let's see if we can do that here like this. Substitute equals. No, not really. I already had all of them. Except D times D, we didn't have that one yet. D times D, that is I times I is minus, and the other minus just falls out. So it is minus 1, it's n. And then obviously we should have... I say obviously, but... What is going on here? This must be a C. It is obvious. I just did it wrong. Obviously, we must have all 4 in every column here. So this is just times the identity. So I and CD becomes I and CD. And this is negating the sign. So C and D swap. And I and N swap. Because they are minus 1 and 1 and minus I and I. And multiplying with C, then C is multiplying with I, so I goes to C. Where are we? Yes. I goes to C, N goes to D. And, we have all 4, so I bet it's correct. n times d. I did it the wrong way around. Why did I do that? Oh, no, I didn't. Times I times n times c times d. Okay. So this is the d times n is c, and this d times c. Looking for d times c. There it is. I. Yeah, it's okay. Go. Okay. I have them all. So if I put, I'm going to put this somewhere else so I can edit it easier, more easy. Oh my god. Okay, so if we put 2 in here, then minus 2 must be in here. Why? Because minus 1 was in here, and if you multiply any element of I with any element of n, then we must get an element of n. Likewise, 2i must be in here, and minus 2i must be in here. But also, multiplying any element of I with any element of I must be an element of I. So 2 times 2, 4, and 8, and 16, and all the powers of 2 end up there. Which then of course leads to the fact that we get here minus 8, minus 16, and so on. And here we get 4i, 8i, 16i, and so on. And here we get minus 4i, minus 8i, minus 16i, and so on. Does things still hold? If now I multiply, let's say, d times d, and I pick 2 random things like this one, that one, and that one, then we get 2 times 4 is 8. The minus drops out, and the I times the I results in minus 1. So we get minus 8. Minus 8 is an n. So d times d is n. Yay, that's correct. So that seems to work. Just by adding the 2 here, everything else, all those other elements are fixed. But this is saying nothing about a 3 or any other prime for that matter. So what if we don't add prime 3 to this one, but we add prime 3 to this one? Let's put it somewhere 3. What is the result of that? Well, that means that 3 times minus 1, that is minus 3. That is then n times n. N times n must be an I. So minus 1 times 3 is minus 3, must be in I. Put it at a random place. Oh, maybe I should put the negative numbers here. Minus 3. Let's put the 3 here. Let's forget about the dot dot dot. We just won't go larger than 16, okay? Just ignore the rest. Well, maybe I stop even at 4. I think it's already a square, it's large enough. So we have 2 and 2 squared, and then I believe it to the power 3, 4, etc. If we add 3 here, then minus 3 must be there. Yeah, it's slowly getting late. As -3 is here, and then of course -3i must be there. And +3i must be here. And -3 times -3, that's both in I, is 9. That's our square. It must be here, because I times I is I. And then -9 is here. So we're really going to put them in that order. -4, no, I don't know. I just put them in a random order. It's like a little random anyway. The order in which I find them, maybe. How about that? Let's put the -3 here. It's actually making more sense. First the 1. So the -3i. Yep, this makes more sense. Yep, and the 27 then is again plus 27i here and minus 27i here. Maybe we should add those, but well, theoretically you can already see the difference. Now let's do even worse. So now we have everything that has a factor of any factor of 2, any factor of 3. The only thing we don't have yet is anything with a factor of 5 or higher primes. Let's put 5 in here to see what happens. Well, that means that -5 then must be in here, right? Because -1 times 5 is -5, and n times c is in D. N times c. N times c must be in D. And yes, that means that here we get no, we can get I by multiplying C times D. For example, I times D is minus 5I. And then this, of course, must be the 5I. We have them all. No, yeah, and then I have to add the squares. So if we multiply this thing with itself, then I times I must stay in I. So that is 25 I squared is minus 25. Is that correct? Yep. And then we have I times n is an n, so this times this is 25. And here we get I don't know, let's do this one just. N times c, pick 5 and 5i is 25i. N times c must be in D, so 25i must be here. And then I bet that minus 25i is in that one. So the only thing that really happens if you, wherever you put a new prime, is that you get a horrible mix-up of the elements of the unit group. Yeah, why not? I mean, I kind of wonder if when it returns, returns to, let's say, a normal integer again. So if you try 5 to the power 3, then what do we get? So this is 125. Is it already 125, or is it going to be 125i or minus I or just minus 125? How do we get something in C? Well, we can figure it out from, it doesn't really matter, anything that ends in C. Pick this one, n times d. So we have to do n, for example, that one, times d, for example, that one. So yeah, minus 125. I times I is minus, and this is 5 times. So minus 125 ends in C. And in D we get I times D, for example, I times D. So that's 125. Ends up here. And in N we end up at D times D. For example, these two, that's minus 125i. And this one is the last one then, 125i. I want to do one more, maybe even two more, to see how this cycles. I think this cycles as long as it can get. If we put the 7 in the last one, you will see something similar. I guess it's just multiplying, of course. It's just the I. You multiply this thing with I, sorry, with something from the identity set. Then it must stay in the same set. So that's a way easier way to do it. So this is minus 3 times minus 3 is that, times minus 3 is minus 27, and that's how we fill the whole thing with powers of 3. And then here we get minus 5i times 5i is 25, and then again times minus 5i is that, and then again times minus 5i is, what the hell is that? 125 times 5, 600 something, 625. Okay, and that is the minus drops out, and that's that, and this is again a minus, so we get minus 625. So then if you ignore the absolute value, then say we call this minus 1, and we call this minus I, and this 1 and this I, then you have all four of them in this case. While here we only have minus 1 and 1 alternating. That's because you put the 3 in here instead of, and here we only have 1, 1, 1, 1. So if you put the prime in I, then I is filled with just one of them. If you put it in N, then you have 2, and if you put it in COD, then you have 4. All 4. Yeah, so we had already minus I, minus 1 and I, so this must be 1, and that is then 625. And we can check that, because that times that, or that squared for that matter, it's even easier. And this one is then minus 5I times minus 125. So that is 625I. And here we have the last one, comma 625I. So far so good. But I really wonder what happens if we add, oh, by the way, now we have also to multiply 2 and 3 with each other, but I don't think that matters anything at all. Let's say we could summarize all of these as just 2 to the power of k, where k runs from 0. So 2 to the power, I'll reuse the same k, although it's a different k. And this is then I times 2 to the power of k. And minus I times 2 to the power of k. Maybe we should line them up like that. So here we get minus 3, but multiplied with any power of 2. So really this is 2 to the power something. It's again a different k, but times minus 3. Well, I could put a minus in front of it. And then we have 3 to the power, and that must then be an odd number. Okay, I'll use a L here, plus 1. And this one is then plus 2 to the power k times 3 to the power 2L. An even power of 3. But isn't that the same as saying minus 3 to that power? It is. That makes super much sense as well. So actually, it's just -3 to the power L. That is all the same. Which then includes that one if you pick L equals 0. So now I can delete this. Yeah. Oh, that's interesting. And what was this one? Here we have 3 or -9 and then plus again and so on. So these we can combine as this is 3 to the power an odd number, and this is -3 to the power an even number. And the power of 2 is just distributed into it. And does change the sign because we already have that. So this is should multiply this with 2 to the power k. And this one too. Is that correct? Well, for k0, then of course we have the 3 for k and L 0. We have the 3, and for k0 and L is 1, we have the 9, the -9, which is correct. And every time L is incremented by 1 here, we get 9, a factor of 9 extra, and then the minus remains. And here we go to 27 and so on, and then it remains a plus. So that's correct. And the 2 to the power k factors is just this from I, so that should always work. Now I think we can combine this as well, because this minus here, you can keep that and do -1 to the power. So I'm going to put a minus in front of it now and do -3 to that power, or to any power for that matter. And then we have that. And that. That cannot be right, however. What went wrong? If now k is 0, then suddenly we have in I and N the same thing. No, it's not true. It's times -1. So this -1 here. Well, if you ask me, then we can extend that to this one as well. this is simply I times 2k times minus 3 to the power L. And that's minus I times minus 3 to the power L. And then you gotta wonder if putting minus 5i here squared, of course. Yeah, it's just this. I put it there and I do it to some power. And we might as well include it here, and then we have everything. And it doesn't change. I think we found a complete partitioning of this thing. You just take for all prime numbers. For all prime numbers, you multiply them with one of these. Random one, doesn't matter. And then some random exponents, so to some random power of that. And then you have all elements of I. And then you simply repeat that because it's a formula. You can just take the exact same formula with a minus in front of it for C and an I in front of it, or a minus I in front of it. The rest doesn't change. Now, see if I can understand if that is true, because now apparently it doesn't matter what you put into here. Why not? Yeah, it's confusing to reuse the same variables while they are really different. So I'm gonna call this K0, and this K1, K2, and K3. And the same here. Because they are all random, or independent, I should say. And if now you take a random element of, let's say, n and c, and you multiply them, well, n times c must go to d. Let's figure out if that is true. So we have a random element, which is random meaning k1, l1, and m1 are unknown. Just some integers, and we multiply that thing with some element of c. Well, that's going to be for some k2, l2, and m2. Then the result of that is, well, that's going to be 2 to the power k1 plus k2 times 3 to the power minus 3. Minus 3 to the power L1 plus L2 times minus 5i to the power M1 plus M2. What am I doing wrong here? No, okay. And an I. That I here. Oh, I missed one. The minus here. So add a minus in front of it. Well, it looks like minus 2 to the power, but it is not. It's minus whatever that is. So yes, of course, we end up with minus I then. And then the exponents just add. So that's 100% closed correctly. For obvious reasons, I would say. Unfortunately, that does not include all numbers. All of these numbers are equal, are either an element of z, or they are element of iz. They are not all elements of I adjoined to z, which is also, I don't know, 1 plus I, for example, 1 plus 2i, 3 minus 7i. So this covers all 4 axes, but not the quadrants in between them. And what I was mainly wondering today, before I even started streaming, was can delete this, just trivial suddenly. I was wondering if this already fixes all the quadrants, or if it can mix those up as well completely. For example, can I add, let's say, the point 2 plus 2 minus 3i? Can I add that point to any of those 4 without a problem? I guess I can, actually, because This number is not an element of any of those four, so I can put it wherever I want. I would say. Pretty messy. So if you consider all such numbers, and then here we covered all the x's, meaning that if you set a to 0, then b can be anything and it's somewhere in here. Or if you set b to 0, and then a can be anything and it's going to be in here. But if both a and b are non-zero, then it's not in here. So I am inclined to say, well, maybe. See, the problem of writing -5 to the power I here is that it depends on m0. If we are in A or in B, if we're contributing as an A or as an B. Because both A and B can be both positive and negative. So they do cover this minus or that minus for that matter. But the I is separated like this. I mean, why? Why would you do that? Haven't seen you in a while. I have the feeling that we might as well define a new thing. It's what is it? It's a monster. That's what it is. A field, a set, a group. I don't know. It's definitely a set. So let's define a set K, L, M, and so on as being as existing of all such things. With the choice of, well, this is just a multiplication of all primes, product of all primes here, and then each prime is either multiplied with 1, -1, I, or minus I. And then all is done to any exponent. That's just enumerating all the elements of that set. Let's just call it S. It's a short. Indexes K, L, M, and so on are implied. Then why would I not say Zi is yeah, that what we had, but now I'm going to replace this with S. Bleep. I think that should hold. I think that enumerates. Both A and B are completely defined, of course. So S is defined. We picked all those signs here. In it, the minus I belongs to the 5. That's fixed. The minus 1 here in front of the 3 is fixed. Then, given those things, S is completely defined as you can enumerate them by changing K, L, and M, just like you could do for Z if all those signs were just 1. So just 2 to the power K, 3 to the power L, 5 to the power M, and so on. That would just be the factorization, the normal factorization of Z. And therefore S would be equal to Z. So it's not the case now that if you choose B equals 0, I'm not even sure where 0 would be, by the way. Do we still have a 0 in here? No, we don't. Okay, is that a problem? Both A and B cannot be 0. Yeah, that is kind of a problem, maybe. So then it's not ZI. I could add the 0 to S, I guess. Why would I need the 0? I don't need 0. I just want a multiplicative group. It's not ZI anyway. That's a good question. What is 0? Is 0 an element of ZI over ZI star? Let's ask ChatGPT. Already chatted about this. Nope. Yeah, this is what I have been talking about already. Let's ask, is 0 an element of ZI? Is the backslash? What is it? This is slash ZI star. Uh-huh. It does feel wrong though. I don't think this is correct. I'm also thinking about vague memory of something. You literally had to remove the 0 in order to get a group. Can't remember what it was though. I'll type it in literally, I guess. I remember vaguely to have seen before that one had to remove the 0 from some set in order to make it a group. Yeah, okay. So it might or might not be, could be added, but I don't think it adds much. Yeah, it's its own equivalence group. That's weird. I would say the norm of this whole semi-group here should be equal to the norm of that thing, aka 4. If you add a 0 to it, and then you have suddenly 5 things. Because, well, 0 has its own equivalence group then. Equivalence, whatever, set, I don't know. Let's not add a 0. Well, interestingly, if we do this, then we don't even have the axis, because neither A nor B are 0. So I would at least have to add these separately. So then you would have, actually, I mean, if we want to make the complete Z, we need to add a 0, of course, for the Z. And now we have A and BI and A plus BI, all separately. Yeah, so since A and B are never 0, none of these is 0. So the 0 is separate. And if A and B are not 0, then, yeah, this is literally A plus 0 times I, so I think these are all separate then. However, A and BI are not different. Oh, they are. Wait a minute. S is just this. S could be like, I could be set equal to S, say. No, now I'm confused. Is it good? It could. I could be set to S, but I'm trying to construct the whole ZI here. And multiply. Yeah, okay. So it. Yeah, I just never stopped digital. I didn't eat. That's why. I should stop though. It's 1 a.m. I think it's correct to have BI in it. For example, if you want to partition the ZI into 4 subsets to form the semi-group, then I could set this I equal to S, and then obviously I times S, because B is also S, would be C. And now I have to wonder, what am I missing? Because if I have if this is S and this is C, and we already saw that this falls outside of all of them, then I'm still missing N and D. Yep, and I am. We are. So we need A and minus A, and B and minus B. I. And 0. And then we're still not done. Because, and of course here we also need plus and minus. So I need I minus BI and minus I plus BI and minus I minus BI. Now I think it's pretty much complete then. My bitrate, let me check. Yeah, I'm gonna stop anyway because yeah, it's too late. View, dog, scene, collection, tools, file, settings probably. Settings, stream, nope, output, bitrate. But yeah, senile, but not that stupid. That's my bitrate in OBS. So much also. Good Jewish. This is the settings. Is that not enough? I think I took some time at some point to figure out what was really needed for YouTube. I mean, if you make it too high, then people can't watch it anymore because they don't have the bandwidth. And it's not too low because if I look at it, it looks sharp enough. Yeah, you have to tell YouTube that you want to. I don't record anything. I just stream. I don't record it. Now you have to tell YouTube that you want to download the high quality, isn't it? I mean, they just send you less bandwidth if they feel like it. For a long time, I had in my description, read the FAQ, and the FAQ said that you have to manually tell YouTube that you want the highest quality, otherwise they don't give it to you, which is really stupid. So if you just save it, or are you talking about your own OBS? Have you been recording me? I mean, YouTube doesn't even allow that, but Wouldn't know how you did that then. So now I don't know anymore. Are you talking about your own recordings, or have you been talking about the recordings that you make yourself with OBS, or did you talk about the recordings that you make of my stream? Oh, okay. So it was not about my thing. Yeah, well, then I showed you the settings, but I never record, so I don't have the hard disk space to record this. I'm just annoying YouTube, yeah. Never deleting this stuff. They must have had terabytes of my videos now, and nobody's looking at it. Such a waste of this space. I'm 8 hours live now. Wow. Yeah, I was going to stop. It's getting too late. I guess that in the future stream or whatever, I'm going to try primes 3, 4, and 5. That should be enough. And then a few powers of KLNM. And then just brute force this. And see if I get every integer exactly once. Or every Euler integer exactly once. And on top of that, then I can even do the partitioning of that. And see if it holds. Just I don't know, just cool. So good night.